the National Cheng-Kung University of Taiwan.
Good afternoon, everyone. My name is Qikwei. I am the second author of this paper, and the paper contributed a lot by the first author, but I present here. The topic of our paper is a comparison of different point density for detecting tree positions of a subtropical forest from airborne LiDAR data. For the introduction, I'd like to say the information of forest structure parameters are important for forest resource management. Here we are referring things like tree position, tree height, diameter at breast height, the DBH. They are the forest structural parameters that we are referring, such as these things. And particularly for this paper, we are looking at the tree position. And recent studies using airborne laser scanners, they are pretty much focusing on conifer forest, such as these papers. And we haven't found much for deciduous forest. In Taiwan, here's Taiwan. These are the surrounding countries, Philippines, Japan, Korea, China, and Vietnam. We are pretty much in the tropical to subtropical climate. So those results from the conifer trees, they are insightful, but not the real case. So we decided to test our own thing here. So we have the data collected, the ALS data collected in May 2009, and it is operated by, it is collected by ALTM, Uptech ALTM 3070 on board in helicopter. And it was 5 meters above ground height, and we have the mean point density of 276 points per meter squared, and that's the real number. The reason we use this high number because we know we are dealing with a subtropical forest, so there will be less penetration of the grounds. So that's we order the highest possible point density possible for our site. And in order to get that much points, so the study area is actually quite small. So as you can see, it's this very little hilly mountain here. You can see this is 300-meter scale, so this is not a very large site. And we calculate point density here. Many of them are actually, most of them are higher than 100 points per meter squared, and some of them even reach 1,000, something like that. So this is very high point density data set. Then here, that's the point clouds of this study site, of this study area, actually, this study area. But for now, we are only looking at this study site. This is a 30 meter by 30 meter squared area where we have ground truth data here. For this particular ground study site, we have the dominant trees as Taiwan cassia, camphor tree, common Inolan coppice, and we have other suppressed trees as common free fern and turning the wind. We have those trees here. For the ground truthing of the tree position, we employed a Faro photon 120, and we have it scanned on May 25th of 2011. So this is actually 2 years after the airborne LiDAR scan. We assume the trees hadn't changed much, so this ground truthing is still valid. And later I'll show you that's quite a good assumption. And we make sure the TOS points are in the same coordinate as the ALS points, so we can match the tree position determined from the ALS data to match those found in the TOS data. And then for the TOS data, the tree position are determined manually by fitting circles from the TOS points at the 1.3 to 1.5 meter above ground. So that's those circles that we cut those points in the point clouds and then fit the circle to that and determine the center, and then we can also determine the diameter too. But right now we're only looking at the center as the tree position. And we found 17 stems in the data. And we also have LAI index measured by using the LAI 2000. On the left hand side, this is the all the TOS points. There are 5 scans there, so you can see this where the TOS were. So it's 1, 2, 3, 4, and 5 up there. And we have this is the ground truthing results. So there are 17 trees here, and here we show a 1 meter radius. And this 1 meter radius is important in our results, and later I'll show that. We assume there's difference between the ALS data and the TOS data, so we kind of use this 1 meter radius as a buffer. If the tree position difference is within 1 meter, then we say that's okay. So this is the site, what the site looked like. Those are the trees, and you can see there are many suppressed trees on the ground. And then that's the top. That's we get the LAI number of 3.95. To extract the tree position from the ALS data, we're actually extracting tree position by extracting tree top. So in the ALS data, that's actually that's the DSM kind of thing. So we extract the tree top and then say that's the tree position. So it is a little bit different than the TOS data. In TOS data, we look at the points at the breast height, but in ALS data, we look at the top. So the tree top detection is by local maximum moving window filter using the canopy height model. And the canopy height model is just the difference between the DSM and DEM. So now, we would like to know what would affect the accuracy of the tree position. So would the canopy height model pixel resolution affect the accuracy, or would the point density affect the accuracy of the tree position? Here we do some tests on the data. Because we have this much higher point density, so this is what we do. First, we create resample data sets with 1, 5, 10, 20, 30, 40, 50, 60, 70, 80, all the way to 100 points per meter squared, so that we can play with the data, and we resample the data and create kind of artificial data sets with those point densities, and they are resampled randomly. And to understand the variation of the results, because if we only do this once, then that was just one shot. So we might as well do it 30 times, so we can understand the variation of the results. So for each of those point density, we repeat 30 times. So that's 30 times, 30 times, 30 times. So we are pretty much doing the bootstrapping method. And then we can create the DSM, DEM, and CHM of those data. And for each DSM, DEM, and CHM, we create them with the pixel resolution of 1 meter, half a meter, and 0.2 meter. And then we test the kernel size, the local maximum moving window filter. We test the kernel size of 3 by 3, 5 by 5, 7 by 7, 9 by 9. Okay, now here I show the points results. That's here you see this is the airborne LiDAR data here. That's the yellow points here, and you see the ground points here. That's the terrestrial laser scanner points. Even though there is 2-year difference, you can see the top of the canopy matches quite well, and also some internal structures has some they show similar structures. So that's why we think that the 2-year difference is fine. Okay. Okay. So I'm sorry. Let's go back a little bit. Here you see that the TOS points scans. They acquire most of the data on the ground, and they acquire few at the top, and they don't have much in the middle. And the ALS data is pretty much on the top of the canopy, and something in the middle, and not much on the ground. There has been a paper using airborne laser data and using the 3D information, everything including those points in the internal of the tree, in order to get the tree position. But as you can see, we couldn't do that because there's too much obscure of those from the structure of the trees. So it wouldn't be possible to use that to determine the tree position. Okay, so here I show these points here. They are the DSM derived from the ALS data, and in the middle here are the colored TOS points. So you can see the TOS is not possible to give a really reliable DSM here. So you can see there's too much missing in between there. And here at the ground, here we show actually there are 4 lines. So one is the TOS derived DEM at the pixel resolution of 0.2 meter, and that's the ground truths. Okay, that's the ground truths. And the other 3 are AOS derived DEM at 1 meter, half a meter, and 0.2 meter pixel resolution. They were all created with the point density of 100 points per meter squared. So what we are showing here is that a good resemblance can be found on the ground. So that's quite good. That's actually quite good. So we are satisfied that even though with this high canopy, this high LAI index, we can still get ground points from the LiDAR data. Okay, so now here we show the DEM result. In the DEM result here, I show the DEM difference. So the DEM difference is the difference between the LS derived DEM and the TOS derived DEM. So here we use the TOS derived DEM as the ground truth. So that's the difference. And for each resampled data set, we average all those difference. So then we create one data in here, and then we repeat this 30 times. So they're supposed to be distributed in here, but we use the box plot to show that variation. So you can see that with 1 meter, half a meter, and 0.2 meter pixel resolutions, all of them show pretty much the same trend. The average difference decreases asymptotically as the point density increases. And also we notice that if we were to use the 0.1 meter, the average difference 0.1 meter as some criteria, then then 10 points per meter squared should be sufficient. And then if we are looking for even higher accuracy, then 30 points may be another choice. And that this variability decreases as the points increases. And as you can see, if we use all the points to create the DEM, then we actually get pretty close result with the ground truth. So that's the DEM results. And then we show the DSM result. So for the DSM result, because we do not have the ground truth collected from the ground for the DSM. So we use the airless-derived DSM with all the points as the truth. So now the DSM difference is the airless-derived DSM minus the airless-derived DSM with 276 points per meter squared. So the counters are the same as the previous one, and then I also show the average difference here. As you can see here, the pattern is pretty much the same. The average difference decreases asymptotically as the point density increases, and also we also notice that the pixel size affects the average difference. So with the pixel size of 1 meter, the green one, it is this the variation is this much all the way to 100 points per meter squared. But with a smaller pixel size, like such as half a meter, the blue one, 0.2 meter, the black one, you can see the variation decreases very much. Okay. All right. So so for the tree position results that we showed, using the 1 meter CHM with different kernel size, we evaluated the omission error and the commission error, and we found with the kernel size of with this one, we found a kernel size of 3 by 3. We have the best results here, and with half a meter CHM, we found the kernel size of 5 by 5. We produced the best results, and for 0.2 meter CHM, the kernel size of 9 by 9 would create the best results. Those commission errors and omission errors, they are within certain range. They are within certain range. So if we compare the best results for each pixel resolution, and we found the best combination would be the half a meter CHM using the kernel size of 5 by 5 for this area. So our conclusion is that for this subtropical forest, I'm sorry for the typo, it is supposed to be a subtropical forest. The LI being 3.95, higher point density produces better DSM and DEM. That's for sure. And we found that the point density of 10 points per meter squared is enough to achieve the average difference of 1 meter, 0.1 meter for both DSM and DEM. And finally, we found that the combination of half a meter CHM kernel size of 5 by 5 seemed to produce the best result. The best result meaning both commission and omission errors are approaching 0.4 asymptotically when the point density is 10 points per meter squared. And this is a work on progress, and we will try to figure out if other combinations will produce better results. Thank you.
Thanks, Chikwai. I'd recommend that questions for Chikwai be asked after the session. And our last speaker for today's session is me. My name's Will Woodgate.